Okay, good morning, or whenever you're watching this. We're gonna start talking about function inverses. So if you notice here, I have the definition. So if you need to pause at any time and just copy this down, great. These are just things that I want you to have in your journal for notation purposes and just for the definition so you can have it on hand. So let's just go through this. This should be recognizable, right? This is a composition, right, of a function. So this is f of g of x, and this is new. So if I can do a composition of two functions and my result is x, then they are inverse functions of one another. If I can do this to both the f of g of x and g of f of x, if I get x for both compositions, then these two functions are going to be inverses of one another. So the notation is g is the inverse function of f, and f is the inverse function of g. So it's notated like this little -1. It's not an exponent. We'll just call it a superscript. It's f to the -1, right? F to the -1, or f of -1. So little hint here, a little note. The domain of one function is the range of the function's inverse. So we'll think about that as we look at this the first two inverses of one another, and it'll kind of help you to see what that means. So hint, in an inverse function, inverse functions are the reflection of each other over the line y equals x. So I'm going to pull up my Desmos here, and I'll show you what that means. So I have two functions here, and I've put them here. I have x minus 4 and x plus 4. So x minus 4 is this red line here, and x plus 4 is this blue line. X minus 4 and x plus 4 are inverses of one another. What I want to do is show you that y equals x line here, and I want to dash it. There we go. How about that one? Yeah. So you can see that the functions are a reflection over. So if this is 0, 4, and this is -4, that's a reflection over this line. If this is -2, 2, I have a 2, -2. So think about what I said just a second ago, that inverse functions are the reflection over the line, but the domain of one function is the range of the other function. So think about that. If the domain x values are the y values of the other function, you can see that in these 2 points. The domain, -2, is the range in the inverse, right? The domain 2 is the range in the inverse. So kind of cool. We can see that here, and let's see if we can add another point. Like, what about this? What about 6 here? So notice we added another one. 6, 2 is here, 6, 2. Let's see if that's true for another point here, because the opposite would be 2, 6, right? Is this 2, 6? It is. So the domain 2 is the range in the reflected function. The range here is the domain in the inverse function. So kind of neat to see that little discovery piece. So in your journal, what I did is I just cut out a little graph here to show that reflection line, f of x equals x, or that y equals x line. And then I did those two lines there. So let's look at how we can verify whether functions are inverses of one another. So you can write this note down here. Verifying inverse functions. You can verify that functions are inverses of one another by composing one with the other and vice versa. So we saw that on the first page, the composition of one function into the other results in x, right? But you have to do it both so they can both equal x. So let's have an example. So let's see these two functions here. We have x cubed plus 1 and the cubed root of x minus 1. I want to just look at them here on the graph first. So we had x cubed plus 1, and we had the cubed root, but on the functions thing, the cubed root of x minus 1. Oh no, this is under. There you go. Okay, that should be under. Okay, so let's look at this. Interesting, right? So I can verify here because my range, oh, this is 0, 1, so it would be 1, 0, wouldn't it? There you go. The domain of my red function is the range in my green function. The domain in my green function is the range in my red function. And look, here's my like overlapping point. That's interesting, huh? So it reflects perfectly across that line. And you guys noticed that a lot when we were talking about the parent functions, that the cubed root and the cubic functions look very similar. Well, this is their relation. They are inverses of one another. Oh, you couldn't see that. Let me show this again. Sorry. Okay, here it is right here. So the domain 1, 0 is or 1 is the range in the red function. Sorry about that. And the domain in the red function is the range. And you can see their reflection point here. So you guys talked a lot about in the discussion post with the parent functions, how the cubic and the cube root look like they're related or they're very similar, which is true because they are actually inverses of one another. So here's how we can verify algebraically whether functions are inverses of one another. So let's see. I want to compose, right? So I'm going to compose f of g of x equals, so I'm plugging in, I'm going to write this so that way you can see the work on the whiteboard. So we're going to do f of g of x equals, so the f of x was x cubed plus 1, and g of x was cubed root of x minus 1. So in that x value, I'm plugging in cubed root of x minus 1, and then outside is plus 1. So now after I simplify this, f of g of x equals, these cancel, okay? So my x minus 1 comes out, and then plus 1 here, they cancel, right? So f of g of x equals x. So that checks out. But now we have to do the opposite, the vice versa, right? We have to do the g of f of x as well, just to verify that they are inverses of one another. It won't always work out is the thing there. So we have the cubed root of that x minus 1. So we have the x cubed plus 1 and then minus 1 underneath. So let's simplify this. We can add and subtract our 1 here, or we have a positive 1 and a negative 1, so those cancel. So we just have a cubed root of x cubed there. We'll look at that. Cubed root of x cubed is just x. So the g of f of x equals x. So when they both verify, then it tells you, here's the work here, you can copy that down. This tells us that they are inverses when they both verify. They must both verify. So here's our second part, finding an inverse function. If I am only given one function and I want to find the inverse of that function, I can do, now what we talked about was the domain of one function is the range of the other function, right? So it would kind of make sense for us to flip the x and y in one of the functions to find the inverse of the other, doesn't it? So here are your steps for finding an inverse function. In the equation f of x, replace the f of x for y, okay, because we know f of x is the same as y. Interchange the x and y, solve for y, and then replace y with the f of that -1, f to the -1, or f of -1 of x. So let's try this. I want to show you the work. I know it's here, and I'll show you that in just a second to let you copy it down. But just watching me work it out might help. So we have a function f of x equals 2x plus 3. We know f of x is the same as y, right? And what did we find out from the table? We found out that the x in one function is the y in the other function, right? The y in one function is the x in the other function. So we can switch these, right? I'm writing the same thing. X equals 2y plus 3. We can switch them and then solve for y. So we'll just subtract our 3 here. X minus 3 equals 2y and divide by 2. So how I would prefer you to write it is putting the y over here and then saying this is 1/2 x minus 3/2. That's how I'd prefer you to write it, as two fractions. You can write it as x minus 3/2. That's still technically correct. All right, so let's replace this y with that f of -1 of x equals 1/2 x minus 3/2. Okay. So here's the work on that. While you're writing that down, I'm going to type this in our Desmos to see if this is actually the case. X plus 3. And I know you can't see it. I wanted to give you a chance to write that down. But here we go. Okay, so let me switch my sharing. Okay. There we go. Okay, so you can see here's our y equals x reflection line. And here's some points here. Here's 3, 0. What about 0, 3? Does that match? Yeah. Oh, look at that. My x and y values are switched. Here's my reflection line. See if there's any other like solid points here. There's a point right there. -5, 4. Let's see if -4, -5 is the point over here. It is -4, -5. So you can see that we verified, and then we verified even further using our graph. So that's a way to find the inverse function. So anytime you find an inverse function, you always want to verify either by graphing, right? Or by doing the composition. All right, that's it for inverses. I think we're going to start discovering what other parent functions have the inverses too. So